Hello viewers, welcome to the live interactive program of CIET NCERT that you are watching on Kishore Manch channel of SWAYAM Prabha. Some of you are also watching us live on our YouTube channel NCERT official, where you can send us your comments and queries in the live chat that is going on below the video. Students like you, other students, teachers and learners have joined the chat and are ready to send their messages. You can start a discussion with them also in that live chat. Also, you can note down our toll-free numbers. In this way, you can also listen to your own voice, ask your questions with our experts in the live session. The numbers are 1800111-265 and 1800112-199. If you want to send us emails and maybe you are getting queries, questions after you are solving some sums of maths or maybe dealing with science problems, and later on you realize that you have a query, you can email us at ciet.kishoremanch@gmail.com as well. So now that we have already said that maths sometimes causes puzzles and sometimes creates confusions when learning at home by ourselves, that's why a live interactive session is much needed. And today we are going to learn a lot about relations and functions, and to tell us more about that, we have with us Dr. Madhu V. Doctor, welcome to the show, sir.
Thank you, Rakshit. So this is our fourth class of relations and functions. So we have many things discussed in relations and functions. Relations and functions, the chapter starts with the relation, the types of relation, then functions, a different type of one function, on-to function, composition of functions, all these things. So now, today we are going to enter into a very interesting area, and which is very useful in future mathematics also. That is called binary operations. Okay. Yeah. Even though the word binary means that two, it is something connected with two, and it is something connected with some operations. Okay. So we are familiar with different types of mathematical operations from their early school also, lower class also. They have studied addition, subtraction, multiplication, division, different operations we have studied. So that time, if you look back, you might have observed some interesting features. So suppose you think of natural numbers and take two natural numbers and add. So 2 plus 3, you will get 5, and the answer will be again a natural number. Right. Okay. But at the same time, if you take subtraction, 2 minus 3, you will not get a natural number.
Right.
The answer will not be a natural number. So it will go out of that natural number set. So there are certain kind of operations. Once you do the operation, take two elements from that set, do the operation, the answer lies inside the set. And there are some operations, if you do that one, the answer may go out, or you may not be knowing the answer at all. Such situations may happen. For example, if you take one more example I will tell. Suppose you take natural numbers again. Take two natural numbers and find the average of them. That is a and b, a plus b by 2. Then what will happen? Average always need not be a natural number. For example, the same example, 2 plus 3. 2 plus 3, 2 and 3, 2 plus 3 divided by 2 will not give a natural number.
Not even a whole number. So it
not even a whole number. So it will be a problem. So there are some certain type of set, and connected with the set, there is an operation. Sometimes the answer will be inside that one. Sometimes the answer may go out. So we are going to concentrate on those operations and sets where this answer, if you pick two elements and do the operation, the answer should lie inside that particular set. That type of operations are called binary operations. Okay. So what we are going to do here is we are looking into binary operations as a particular type of function, because functions, all of our viewers are familiar. They know what is a function, when a relation become a function, all these things they are familiar. So I'm going to treat our binary operation as a function. A binary operation on a set is a set A. You will denote it by different methods. You can, it may be addition, it may be subtraction, it may be you can define a new operation also, like average, which you have just explained. So what you can do is you can denote it by a star. So star is a function from A cross A to A. So whatever the condition it should happen, it should be a function from the set A cross A to A. So you take any two elements from, or any element from A cross A. Elements in A cross A are actually ordered pairs. So if you take them, it should be mapped to some element. You denote it by A star B. It is only a notation. In case of addition, it will be plus. In case of multiplication, it will be product times. In case of division, it will be division operation will be there. Like that, it will be different operations. So what is going to happen is it will be denoted by A star B. So this is just, we'll go through some examples which are familiar to everyone. So addition on natural numbers. It is a binary operation. You know that if you take two natural numbers and add, your answer will be a natural number. Subtraction on integers. Just now we have told that subtraction on natural numbers is not binary, but on integers, it will be a binary operation. Okay. Now, similarly, multiplication on Q. To take two numbers and multiply, two rational numbers and multiply, the answer will be again a rational number. And again, subtraction on R is also a binary operation. Now, I have a question here to the viewers, that what about division on real numbers? So think about it for some time, whether the division will be a binary operation or what are the properties the division will have. We will come to that one again. Let us see one more example that is also for viewers. Very easy one. I have given a set A equal to 1, 2, 3, 4. What you have to do is you have to define a binary operation on A. So what you should do, you have to write all possible pairs. You have to take 1, 1 and do some operation and get an answer from capital A itself. 1, 1 can be any value which you are thinking. You can give any value. You can add, subtract, all the things. But remember, where the answer should be, what you are getting should be in A. So try to write, take a sheet of paper and try to write down one example yourself. Now, I will give one example for that one. Here, what I am going to do is I am taking A star B and defining A star B as minimum of A and B. So you take any two elements from capital A, say 2, 3, 2 and 3, ordered pair 2, 3, you take, or 2 star 3 you take. 2 star 3 should be minimum of 2 and 3. So now question for our audience is it a binary operation? Is it a binary operation? That means if you take any two elements from this set A equal to 1, 2, 3, 4 and do the operation that taking the minimum, again will the answer will be in capital A or not? That is the question. I think it is very easy. You are taking minimum of two numbers. Even I think lower class students can answer that one. Need not be a class 12 student, but they can answer very easily. Okay. Now, one more question in the same line. You have a set, little bigger set. A equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, what I am asking is A star B is equal to greatest common divisor of A and B. Okay. Greatest common divisor of A and B. Is it a binary operation? So to make binary operation, what should happen? You take two elements, randomly you take two elements and check whether they are GCD. Sometimes they call HCF, highest common factor. The greatest common divisor should be again in capital A. It should happen for every pair you choose. Now, what happens if you replace your GCD with LCM? Least common multiple. What will happen? So, is it a binary operation? Think about it. If you take 3 and 4, 3 star 4, find its LCM. What will happen? Just think about it. Now, at this stage, some of us maybe have a feeling that all this what we have discussed is about natural numbers, integers, whole numbers, or number system which you have studied in lower classes. Maybe 9th standard they have looked in number system as a whole number system, and in their class 11 they have studied the Venn diagram of number system. Smaller one is natural numbers, then whole numbers, then it will go like that, circle, circle, circle. They might have drawn the Venn diagrams. Okay, so whatever we have done is based on numbers. Does this kind of things can be extended to other than numbers anywhere? That is what we are going to show you now. The question is, suppose I have a set capital X. Okay, I have a set capital X. And you think about P of X, the set of all subsets of the set X. So viewers may be remembering its name. It is called power set. P of X is called power set. So in sets also you have studied many operations. There was some section called algebra of sets like that. So they might have studied in class 11 that different operations on set. So one operation is union. So my question is union a binary operation on P of X? If you take two elements from P of X, not any set, two elements from P of X and take their union, will it be again in P of X? Okay, that is one question. Automatically, other question will be, is intersection a binary operation? Okay, is intersection a binary operation on P of X? Okay, now let us see another property which they have already studied in many earlier also. Suppose you take two natural numbers, and in natural numbers you define the operation addition.
Right.
So you take two numbers, 4 plus 2, you will get an answer 6. You interchange the order, 2 plus 4. You are going to get the same answer. Okay, so 4 plus 2 and 2 plus 4 is same. That is, order does not matter there. Now you look into the other set like integers. Subtraction. Subtraction is a binary operation. You take two elements, 2 and 3. 2 minus 3 you can calculate, you will get an answer. At the same time, you take 3 minus 2. You will get an answer. The answer is again an integer, but answers are not same. So there are some particular type of operations when order matters and where order does not matter. So what we are going to name that particular operation as commutative operation. So a binary operation star on a set A is called commutative if A star B equal to B star A for every A and B in A. It should happen for every element, not for one particular A and B. It should happen for every element. Okay. So we have addition on integers is a commutative binary operation. Okay. Subtraction of some say real numbers is not commutative. Integers it is not commutative. Similarly, another example is I am defining a new operations. Okay, that is what one interesting thing in this one is you can construct your own operations. Okay, now I am constructing one operation like on real numbers. Take any two real numbers. My operation is A star B is equal to A plus 2B. First element is A as it is plus 2 times of second element. Okay, it is not commutative. I think you can answer why it is not commutative, because if you interchange B star A, B plus 2A will be there. A. So it is not, they are not equal. Generally, they are not equal.
They are specific to their order.
Specific. Their order is very important. So the relation is not commutative. Okay. Now, let us see the earlier one problem we have seen. A equal to 1, 2, 3, 4. And star is defined as minimum of A and B. A star B is equal to minimum of A and B. The first question is it commutative? You can think about very quickly. That is what you are going to do. You are going to take two elements, 2 and 3, take the minimum. What about order? If you interchange order also, minimum is not going to change. So it is not going to change. So it is commutative. Now, what is interesting thing I want to discuss, once again I came back to this one, is because of this reason. I want to see what is the operation table for a commutative operation. So, okay. So operation table is not only in the medical field, we mathematicians also have operation tables. So we will see that one. So it will be, it is a rows will be there, columns will be there. In the first top row, you will enter all the elements in that set 1, 2, 3, 4. First column 1, 2, 3, 4, and star will be denoted here. What is the operations you are going to do here? And operation is minimum of A and B. What you should do? I want to fill this first box. So what I will do is 1 star 1 I will calculate. 1 star 1 is minimum of 191. Minimum of 191 is 1. So I can write here 1. Like that, I will start filling each column. 1 star 2, what is that one? Here. 1 star 3, what will come here? I will write here. So if you proceed like that, you are going to get this answer. I think some of our viewers might have tried this one just before, so they can check their answer now. Now, what is very interesting thing in this one is, you look into this first row and first column. They're identical. 1, 1, 1, 1, 1, 1, 1, 1. Second row and second column, they're identical. So third row and third column, it is also identical. So what we observed is, if you draw a diagonal line through this here, a diagonal line to this operation table, it is symmetric with respect to that one. Whatever comes on the upper side, it is same in the same order, it will be there. You see, this is the diagonal line, 1, 2, 3 here, here also 1, 2, 3. So it is symmetric. The operation table will be symmetric with respect to this one. Okay, so this is a very interesting feature which we have seen in the commutative property. If you have an operation table, the operation table should be symmetric with respect to that main diagonal entry. Okay, now another interesting feature which we have already studied about numbers is another property is called associativity, because all of the students are familiar with this kind of operations. I did not spend much time what is associative with example. If you take 3 elements and do the operation, say addition in case of natural number, that is the easiest one everyone can check. 2 plus 3 plus 5. You add 2 plus 3, then add 5. Or you keep 2 aside, 3 plus 5, then you come back to 2, 2 plus 3 plus 5. Whatever order you do, it is immaterial. That means you can associate them. So a binary operation is said to be associative if A star B star C equal to A star B star C for every A, B, C in A. Again, this property is for operation, so it should be true for every elements.
Right.
Okay, this is binary associativity. Okay, clearly you can check addition and multiplication on R are associative, which already these all our viewers have studied in their high school classes. Now, subtraction is on R is not associative. Okay. Now I have the question again. I am coming back to that question once again. What about division? Is division associative? Is division commutative on R? The problem is division is not a binary operation at all. Okay, division is not binary operation because what is binary operation should satisfy? You take any 2 elements, you should be able to do the operation. The answer should be again in the set. So for example, if you are thinking of division 1 and 2, we can speak about 1 divided by 2, no problem. But 1 and 0, 1 divided by 0 is not defined. Yeah. So division is not at all a binary operation. So if it is not binary operation, you need not worry about whether it is commutative or associative. Nothing. You need not worry about such things. So, but at the same time, if I take R minus 0, if I remove 0 from my set, real numbers, division is binary operation, but it is not commutative and it is not associative, which you can check very easily. You can give some check with some examples. So it is not associative. Now, I have again coming back to the previous example which we have done. A star B equal to A plus 2B is star associative. So you can try with A star B, you can calculate first. Star C you have to calculate. Then what should do? A star B is A plus 2B plus, again star you are coming. So it will be A plus 2B plus C times, it will, 2 times C will come. Okay, 2 times C will come. But if you change the order, means A is there, B star C already you calculated, B star C will be B plus 2 C will be there. A star B plus 2C will be A plus 2B plus 4C. So you can write down in the paper and check that one. So it is not associative. By this place, many of you might have got a doubt. Whenever we speak about this one, commutative operations you have seen, associative operations you have seen, and we have seen some non-examples for associative operations. But all these non-examples for associativity was also non-example for commutative. For example, subtraction was not commutative in real numbers, not associative. This particular example which we are showing here, it was not commutative, now it is not associative. So you may feel that, okay, these two always come together. It is a package, but need not be. That is what we are going to ask. Think of a binary operation which is commutative but not associative. Okay. Anyway, since time is very less, I will give the answer. You try this one. A star B equal to 1 plus AB. Check whether it is commutative. Check whether it is associative also. Okay. Now, with this one, what we can go for the next property of the binary operation, which is also very familiar one. Students are familiar with this one. It is called identity. A set and an operation is there. Whether this has an identity element. So for example, we will come to the example, which without reading the definition, you can tell many of our viewers will be remembering what identity means. You may be remembering that in addition, 0 is the identity. But here we should be very careful. Addition where you are doing. If you are speaking about addition in natural numbers, it does not have identity element. Okay, because natural numbers does not contain 0. Suppose multiplication on real numbers, it is 1 is your identity element. So like that, so once you make in the definition form, given a binary operation star from A cross A to A, an element E in A, if it exists, is called identity for the operation star if A star E equal to E star A, which is equal to A for all A in A. Now you can check some examples. 0 is the identity for addition on R. Okay. Now immediately once you speak about this particular example, means a particular case of identity, some of our viewers may be quickly remembering something called inverse. For example, you are in integers. 2 is a number. If you add -2, 2 plus -2, you will get 0. 0 is the identity for the operation addition. Okay. So there is something called inverse. So for example, for non-zero real numbers, operation is multiplication. So 1 is the identity. So if you think about 2, you can find an element in non-zero real numbers such that 2 times that element will give you 1. It is 1 by 2. So that is what we want to tell about inverse of an element. Okay. So even though definition is little lengthy, it is not very complicated. You can very easily remember the examples which I have given. Given a binary operation star from A cross A to A, so with identity element E in A, remember the set should have, if you want to speak about invertibility or inverse, the identity element should be there. So you need not worry about inverse of an element in natural numbers with addition, because 0 is not there, identity is not there. So whenever identity element E is there, then only you speak about inverse. Okay, given a binary operation star from A cross A to A with the identity element E in A, an element A in capital A is said to be invertible with respect to the operation star if there exists another element B in A such that A star B equal to E and B star A equal to B star A, and B is called the inverse and is denoted by A inverse. A inverse. Okay. This is, they are familiar. For example, if you take, again, I will come back to the same example just to remember that one, get the idea of that one. If you take real numbers, operations addition, you think about 5, -5 is its additive inverse. You sometimes call additive inverse. Since operation is addition, it is called inverse here. So for -6, inverse will be 6. So -A is the inverse of, for A in the, generally I can tell this one. Okay. Similarly, for multiplication case, if you take a non-zero real number, okay, 1 by A will be the inverse of A, where A is non-zero. Okay. Remember, multiplication is a binary operation on R. So, but non-zero elements only will have inverse. Right. 0 will not have inverse. Okay. Now, some interesting observation, that is one interesting nature of science as well as maths. You have to observe something and you can generalize something. Suppose you think about natural numbers and the operation is multiplication. Okay. You are on natural numbers and operation is multiplication. Then identity element is 1. Right. 1 has an inverse. Inverse of 1 is 1 only. 1. Okay. Now, similarly, suppose you go for whole numbers. Whole numbers, you take the operation addition. Okay. if you take whole numbers and take the operation addition, identity element is 0. Okay, because 0 is a whole number, so identity element is 0. 0 has inverse, 0 is the inverse of 0. So sometimes in a general way, sometimes you may feel that this identity element exists, then identity element will be its own inverse. Okay, every element, if suppose the identity element exists in a set, that element will be its own inverse. Inverse of an identity element will be itself. That you may observe that one. You can check it later in higher classes. You will be proving that kind of properties, and very interesting properties are there regarding that one. Okay, now we'll go to one more problem. This problem you have to think little. That is, this problem is very interesting. That is one reason we are putting that problem, because we have to think. Sometimes we call out of the box. Okay, it is not out of the box actually. You have to go back to your class 11 concepts and look into that problem to solve that one. That is sometimes we call integrating different concepts. Okay, the question is, the set A is 1, 2, 3, 4. You have done one example binary operation. Some of you might have write down yourself, and we have defined one operation called minimum. Now what we want to do is how many binary operations are possible. I'm not asking to write down all binary operations. I'm asking how many binary operations are possible. So let us see the solution. Okay, so you try to draw the operation table. Manually writing everything is very difficult. You will see why it is difficult. Now my job is to fill these boxes. So the first box I want to fill. Okay. Only condition for binary operation is if you do 1 star 1, the answer should be from 1, 2, 3 or 4, any number.
Okay.
Any number from. So here you have 4 choice. How many choice you have? You have 4 choice. You can fill any among the 4 numbers. Okay. Here also you have 4 choice, because the condition don't say it should not be repeated. We can repeat, no problem. So here also 4 choice. Here also 4 choice. So all 16 columns, boxes have 4 choices each, and the answer will be 4 to the power 16. So you need not try that one to write down. So, okay, if it is 4 to the power 16, it's a very big number. Okay. Now, let us see an extension of this problem, little more. So, how many different commutative binary operations are possible on A such that 4 is the identity element and every element is its own inverse? Okay, this problem is little lengthy. What it is given is how much, what are the things we have to check? Set is A equal to 1, 2, 3, 4. Your operation should be commutative. It should be a binary operation. It should be commutative, and 4 is the identity element and every element is its own inverse. So at a stretch you may not be able to complete it quickly. So what we are going to do is we are going to solve it one by one. Okay. I'm going to write this one. Identity is 4. Only that condition I'm giving. So when identity is 4, when you take 1 star 4, answer should be 1. 2 star 4, answer should be 2. That is the definition of identity. 2 star E should be E. So sorry, A 2. 2 star E should be 2. So 2 star 4 is 2. 3 star 4 is 3. So these columns are already filled. Okay. If I put the condition identity element is 4, these are filled. You have freedom to fill these only. So there is only 9 boxes. 9 boxes can be filled in 4 raised to 9 ways. But question is not complete. Just I put that identity element is 4. Now, what about A star A is also 4. For every A, or A star A is 4. Then 1 star 1 should be 4. 2 star 2 should be 4. 3 star 3 should be 4. So this diagonal entry is also filled. Okay. Now we have 1, 2, 3, 4, 5, 6. 6 boxes left out. So once it is 6 boxes left out, then it can be filled in 4 raised to 6 ways. Now come to the last part, commutativity. So commutativity, we have observed that once you fill this something, any number you fill here, automatically you have to fill this column also with the same number. If I fill X here, I have to fill X here. If I fill 2 here, I have to fill with 2 here. So I don't have freedom to fill these columns myself. I have only freedom to fill these three columns, X, Y, Z. These columns I can fill. These columns can be filled in 4 ways. So it can be done in 4 raised to 3 ways. So from 4 raised to 16, we reduce to 4
raised to 3
cube. Okay. So this is one interesting problem in binary operations. Okay. Now, what we are there are many other problems are there in the textbook. They can try those problems and then can come back to, they can ask the answer. Even the YouTube, they can ask the questions, their doubts, we can try to answer. Now, I think we are in the almost end of this particular binary operations, and the whole chapter is coming to end. So we will just quickly go through 1 or 2 problems from some interesting problems from functions.
Right, sir. Before we proceed towards the problems, there's a query for you, and it's about identity. You described in the definition, there was a particular phrase that you used. If it exists, what does it mean?
Yeah, for example, natural numbers.
Right.
Natural numbers and your operation is addition. Okay. It does not have identity. Okay. So that is why when I want to speak about inverse, I think that is the place where I use if it exists. Okay. When you are speaking about inverse, the first thing I want to verify is whether the identity exists or not. So in case of natural numbers, the operation is addition. I will not be worried about inverse because identity does not exist.
Okay.
Okay. So I think I'm clear that.
Right, sir.
Okay. So we'll quickly go through some very interesting problems from functions. Okay. Some selected problems. So why these problems are chosen is these problems give you a new vision to look into that one. Functions, many things you have studied. So what we are going to do now is inverse of functions. Okay, that is many times students may get stuck also. That is why we will come back to this these problems. I choose these problems, and these problems follow a chain. Okay, let us see the first problem. F is a function from R to R defined as f of x equal to 2x minus 3 inverse of, find the inverse of f of x. Okay. So many of you may be remembering, or you might have done substitute y and do this one. But what we are going to do here is a simple visualization of that one. Okay. What you have x. You are starting with x and you are coming to f of x. F of x is 2x minus 3. So what are the things you have done with your x? The first, what I did is I multiplied with 2. You remember what I am doing there. I multiplied with 2. Then I subtracted 3. So 2 operations I have done with x. Multiplied with 2, then subtracted 3. It is now what I am going to do is you can easily remember that suppose somebody you are getting a gift on your birthday. Okay. Somebody has purchased some beautiful gift and wrapped it in a paper, and again they wrapped with a cover, and again they wrapped with a cover. Sometimes we'll cover with 3-4 covers and you give to you. So the gift is there, you put it inside a box, then cover, then cover. Okay. Which cover you are going to open first? The last cover. Right. You are going to open the last cover. So you have to work backward. That is the key. So what I am going to do is I am going to take x. The last operation was subtracting 3. So I have to open that cover. So I will add 3. I will add 3. The next one was multiplying with 2. So I will divide with 2. So this will be the inverse. Okay. So how to check it is inverse? You just take f composition f inverse. You take f composition f inverse, the answer should be x. And f inverse composition f you have to calculate, the answer should be x. This is the first question. Let us see the second one. F is equal to x minus 1 whole square plus 2. Find the inverse. Okay. So what we are going to do is the same process. This time I am not taking much time. X. First I subtract, then I square, then I add 2. So there are 3 covers. Subtract 1, square it, then add. So in reverse, I will take x, subtract 2 because here it is added 2. So here I will subtract 2. Then here it is square. So here I will take square root. Then I will add 1 because here it is minus 1. It is plus 1. So the inverse will be root of x minus 2 plus 1. Here I want to add one more thing. I have not mentioned what is domain and what is codomain of my function. Okay. Usually when we speak about function, we will speak about domain and codomain. But I did not mention purposefully. Once you are not given domain and codomain, we will assume. I'm not saying okay, correct. I will assume it may be R, but it may not be complete R because in case of inverse, all real numbers you cannot give here. So looking at f inverse, you can think about the range of my f of x. So from where to your function is defined. Actually, your function is defined from R to the set 2 to infinity. Okay, it is 2 to infinity. Any real number greater than 2 will be its range. So if you look into the third problem, x square minus 2x plus 3, this chain business will not work. Okay, because if you take x, what will happen? X square is there. You can square it, you can multiply, but it is not as a chain. It is not going as a chain. But then you will apply something called completing the square. You can look into this one and you can say that it is x square minus 2x plus 3 will be equal to x minus 1 whole square plus 2, which is the previous problem. I choose this problem only. Now it is in the chain form. You can solve it very easily. You will get this answer. Okay. Right. Now, one more problem. Always this method will not work. That is what we want to tell. Always this method of mental calculation, the covering, what we call gift wrapper method, I'm calling that method. That method may not work. Then what you will do? Here I have a function f of x. I have not given domain and range. Students can think about what will be its domain. Okay, what will be its range. Then you can see about f of x, how to do that one. You will do x minus 1 by x plus 1 equal to y. Then cross multiplying and simplifying, you will get x equal to 1 plus y divided by 1 minus y. Looking here, you can tell what is its this function's domain, and that domain of inverse will be the range of the given function. So this is one method to solve this type of problem. There are a lot of problems there, but anyway, if you go to that problems, it will take a lot of time. So I think we don't have much time. Any other questions?
Sir, we have 2 minutes left. Why don't we leave our viewers with some assignment or some task for them to be done that they can deliver us at ciet.kishoremanch@gmail.com for you?
Yeah, they can think of a function x divided by 1 plus x square. Okay, think of a function x divided by 1 plus x square. Try to prove it is it a function which is 1, 1 and onto. My question is it a bijective function? Is it 1, 1? Is it onto? The function is x divided by 1 plus x square. They can try it and give the answer. So the whole chapter, what we have studied is, we have studied about types of relations. We have different equivalence relation. One means reflexivity, symmetry, transitivity, and many problems they have studied, solved there also. That is one thing they have studied. Then they studied about functions, 1, 1 function, onto function, many one function, into functions, bijective functions, and using that one they studied composition of functions. Okay, I have one more question for them. If you are taking a set of real numbers to set of real numbers, you define the set of all functions from real numbers to real numbers. Set of all functions from real numbers to real numbers. Okay. And I'm defining an operation, say composition. Take two functions f and g, take f composition g. Again, the question is it a binary operation? Is it a binary operation? Is it a commutative binary operation? Does it have an identity element? Is it associative? So all the property which you have checked, you can check with this particular example. Okay, so these are the things we have studied today, and invertibility, binary operations, all these things you have studied. So once again, what I am telling is they can ask their questions to me in their to my mail ID also they can send
so I have shared a mail ID of CIET with them, and sir, thank you for joining us. You have taught us in detail about binary operations today. And viewers, you have also so many questions in your minds that you can send us at ciet.kishoremanch@gmail.com or at our toll-free numbers when sir joins us next time. I hope you are going to follow suit, and please do those assignments that sir have provided you, so that next time you come up with more questions and queries than ever before, because this time you were just listening. Maybe next time when you have done the exercises, you may have questions for sir. So thank you for joining us today.
Thank you. Thank you.
And viewers, for you, we have next a webinar, and after that at 5 p.m. today, combating procrastination and lethargy during the pandemic will be our Sahyog guideline program for you. Please join and watch that, and keep watching Kishore Manch.